Secondary storage. Although clouds usually do mean rain, computers can make more accurate forecasts by comparing the most recent weather patterns with the vast numbers of previous measurements stored in their memory banks. The operators in the control room of a busy railway network must have rapid access to details about timetables, the location of trains, the goods they are carrying, and so on. While the trains are making their journeys, the information held on the computer must be continually updated and corrected. This picture was taken directly from a television set linked by a telephone to a central computer using Britain's Prestel information retrieval system. Details about an enormous variety of topics, ranging from art exhibitions to flight reservations, must be stored systematically so that each one can be accessed immediately when it is requested. Weather forecasting, vehicle scheduling, data retrieval. For these and many other applications, computers need ready access to large volumes of information. Before looking at the various storage units available, let's see how information is stored inside a computer. Information read into a computer first enters the small, fast, short-term memory inside the central processing unit. It can then be transferred for later use to the large, slower, long-term memory known as secondary storage or the auxiliary or backing store. Computers are designed, therefore, so that the information can easily be transferred between the central processing unit and the various secondary storage media. In order to compare the features of the three most important of these, tape, disk, and drum, we must first look briefly at how information is stored inside a computer. For example, a company's staff list could be stored in the computer in a file with its own label, enabling it to be easily referenced. The first record in this file will contain all the information about the first employee on the list, Robert C. Abel. Each record in a file is made up from several items of information. In this case, the employee's name, address, position, and code. Each item is a combination of different alphanumeric characters, letters, numbers, and punctuation marks. So to understand how a computer stores information, we must first see how characters can be translated into a form that a computer can understand. Inside a computer, each piece of information is stored and transmitted as a binary digit, or bit. A bit can have only two values, 1 and 0. Rather like Morse code, different combinations of ones and zeros are chosen to represent different characters. Secondary storage devices operate magnetically. In some devices, each bit is like a small compass, an upward pointing arrow representing 1 and a downward pointing arrow representing 0. Another way of encoding the information magnetically is for small patches to be magnetized or unmagnetized relative to the surrounding material, indicated here by the presence or absence of a red star. In many coding systems, the bits are grouped into sets of 8, called bytes. Each byte can store one character by using a unique combination of ones and zeros. Every computer stores and transmits bits in groups called words. Small computers may only have 8 bits in each word, while larger ones may have 16, 32, or even 64 bits in a word, enabling several characters to be transmitted and stored together. We must explain how the word length of a computer affects its storage capacity, because this in turn is related to the storage capacities of the secondary storage devices which it will use. The computer's main memory is like a set of numbered boxes, each of which can hold a certain amount of information. The numbers on the boxes, which in the computer would be coded in binary, are their addresses. The computer refers to a box by its address, not by its contents. For a computer to be able to retrieve the information stored inside a box, each box must have its own unique address. If the words in a computer only had 2 bits, the computer could only refer to 4 different binary addresses: 00, 01, 10, and 11. Obviously, the more bits there are in a word, the more addresses the computer has available for labeling the memory boxes. A computer with a 4-bit word could assign unique addresses to 16 different boxes. An 8-bit word can hold 256 different addresses, a 10-bit word 1024, and a 12-bit word 4096. As the number of bits in a word goes up by 1, the number of possible addresses is doubled. The capacity of a memory, or the amount of information it can store, is measured in kilobits. A kilo is not equal to 1,000, but to 1,024, or 2 to the power of 10, the number of addresses which can be referenced by a 10-bit word. 1 mega represents 2 to the power of 20, which is approximately a million. The storage capacities of the magnetic media, tape, disc, and drum, are also measured in these units. It would not make sense to link up a high-capacity storage device, such as a hard disk, to something like a short word-length microcomputer. Another important consideration when choosing which storage device to use is the access time. Hi-Fi provides a good illustration of access time. Suppose you wanted to listen to the 4th track of an album. If the music was recorded on a record, you could place the stylus at the beginning of the right track. However, if the album was on a cassette, you would have to run through the first 3 songs before reaching the one you wanted to hear. Secondary storage devices, similar to records, have a far shorter access time than the ones similar to cassettes. The ideal secondary storage device doesn't exist, but computer engineers are aiming for low cost, high capacity, a short access time, a high rate of transfer of information between the storage unit and the central processor, and something portable, easy to transport from one place to another, and compatible with different computer systems. Throughout this presentation, we shall use these criteria for comparing tape, disc, and drum. Magnetic tape, similar to that used for recording music, is a very popular storage medium. Magnetic tape is usually just over 1 centimeter wide and is stored on reels which may carry up to about 1,000 meters of tape. The information is stored magnetically in a thin layer on the surface of the plastic tape. Information is transferred between the tape and a computer by a machine called a tape drive. Tape drives look very similar to ordinary tape recorders, although they can operate at far higher speeds. 2 reels are mounted on a tape drive. The file reel is the one which the computer operator has mounted in response to a program's demand. The machine reel is linked up to the computer. Large loops of tape are left as buffers in order to reduce the stress on the tape as it starts and stops, and to keep its speed constant across the read-write head. Since the read-write head can either read information from the tape into the computer or write new information onto it, but not both at once, the operator must determine in advance whether reading or writing will be taking place. This can be done by using the plastic write enable ring. If information is to be written onto the file tape, then the ring must be inserted. The ring is removed when information is to be read from the tape. This precaution helps ensure that valuable information stored is not overwritten by mistake. So, to update a tape, A computer needs at least 2 tape drives. One of them holds the old tape, whose information is copied into the computer's main memory. The necessary alterations are made, and the information is copied from the memory onto the new tape. The first tape can then be used again in another run, although it is a sensible precaution to keep it until the new tape has been checked. Large computer installations need extensive tape libraries. Each tape must be carefully numbered and labeled to avoid confusion. As an additional precaution, tapes have a magnetically coated identification mark at the beginning. Information is stored along the tape in parallel lines by rows of magnetic spots, which can be set to represent either 1 or 0. 1 character or byte is stored in each column or frame of single bits running across the width of the tape. Several different coding schemes are in use. In this 9-track tape, the characters are coded in 2 groups of 4 bits each. The extra track, shown here in red, is reserved for the parity bit. The parity bit, which is set automatically by the computer as information is written onto the tape, helps to check against errors in reading and writing. For a machine using odd parity, the total number of bits in each frame must be odd. For example, in the first character shown here, 5 of the bits are set at 1. Since this is already an odd number, the parity bit is set to 0. However, in the second frame, only 4 of the bits are set at 1, so the parity bit must also be 1. So the total number of bits in the frame is odd. If a bit is misread, perhaps because of dirt on the tape, the total number of bits will no longer be odd, and the computer will report that an error has been made. Information is written onto the tape as records, which may be of the same or different lengths. For example, one way of coding the employee records, which we have mentioned earlier, would be to make one record on the tape correspond directly to one employee record. The records are often grouped into blocks separated by an empty space on the tape, called an interblock gap. All the records in a block are either read or written at one go. This means that data can be transferred more efficiently. Depending on their length, more than one file can be stored on a tape. They are separated by end-of-file marks, abbreviated as EOF, and identified by header and trailer labels. The labels include the file name, the details of block size, record length, and so on, to help ensure that the correct data set is being referenced. Cassette tape recorders can be linked up to microcomputers the same way that tape drives form part of a larger system. Compact cassettes are more convenient than reels of tape, although they cannot hold nearly as much information. Programs, as well as data, are frequently stored on cassettes. There are 2 ways of coding information. On special computer tapes, the information is recorded as a sequence of binary dots. However, good reliability can also be obtained by using ordinary audio equipment and representing binary 1 and 0 by 2 different sound tones. The information is stored in units called records, although these do not necessarily correspond to the data records which we discussed earlier. One way of checking the data is to duplicate each record. The second, redundant record, is only used if there is an error in the first record, possibly caused by damage to the tape. For example, at the top, the redundant record can be bypassed because the first record has been read satisfactorily. In the second row, an error in the first record means that the redundant one must be read instead. However, in the third example, errors in both copies of the record mean that it cannot be read at all. Real magnetic tape remains a popular secondary storage medium because it provides a cheap and compact way of storing large volumes of data. Tapes can be stored offline, that is, without being linked up to a computer, and can easily be transported from one location to another. The main disadvantage of tape is its long access time. Because the information is stored sequentially, accessing one particular record involves passing through all the preceding information first. Tape cassettes, in particular, suffer from the drawback of a very slow rate of information transfer to the central processing unit. Magnetic drums were designed to provide the facilities of tape without the disadvantage of long access time. Imagine the information held on a secondary storage device to be like a row of houses, each with its own number or address. For a sequential access medium like tape, finding house number 6 would mean visiting each of the first 5 houses. A random access device, such as a drum or disc, would be able to go directly to house number 6. Whenever a piece of information is stored on a random access device, the time taken to locate it is virtually the same. On a sequential access device, data stored near the end take far longer to reach than data stored near the beginning. Drums are constantly rotating metal cylinders with a thin surface coating of magnetic material in which the information is stored. Although details of their construction vary, all drums operate on the same principle. The drum rotates past fixed read-write heads placed close to its surface. The information is recorded magnetically in tracks running around the drum. The tracks are divided into cells, each storing one bit of information. Although drums are a relatively expensive, low-capacity storage device, the extremely short access time and high transfer rate mean that drums are useful in large computer installations in which frequent reference must be made to stored data and programs. Magnetic disks provide a more flexible version of drum storage. A magnetic disk pack is a stack of flat, circular metal disks. Except for the extreme upper and lower surfaces of the pack, which could be easily scratched, both sides of each disk can store information in a thin magnetic coating. In large computer systems, permanently installed disks are used for storing information which is in frequent use. Exchangeable disk packs are smaller but provide a greater flexibility. Like tapes, they can be mounted onto one of a set of disk drives by a computer operator when requested. As shown here, the read and write heads for each surface are often mounted on linked arms, which move in and out between the edge and the central hub while the disks revolve continually at a high speed. This arrangement means that any particular spot on a disk surface can be rapidly reached by a head. Information is stored in concentric circular tracks around the disk faces. The tracks are divided into sectors so that the location or address of relatively small amounts of data can be identified by specifying the track and sector numbers. The access time depends on 2 factors: the time needed to position the read-write head over the correct track, and the rotational time, which is the time taken for the disks to rotate so that the correct sector is underneath the read-write head. Instead of storing consecutive records next to each other on the same disk face, they are often written onto several disks on tracks lying on the face of an imaginary vertical cylinder. In this way, a substantial amount of information can be transferred in a short time, while the read-write heads remain stationary. The units to the right of the screen of this microcomputer are disk drives. Just as small computers use tape cassettes rather than reels, so flexible disks, known as floppies, have been designed as a smaller, cheaper alternative to hard disks. Floppy disks are made in two different sizes. Regular ones are about 20 centimeters in diameter, while minis are rather smaller. The disks themselves are made of flexible plastic, coated with a thin magnetic layer for storing information. Since the surface is delicate and easily scratched, floppies are always kept and used inside a protective cardboard envelope. This can easily be labeled to identify the disk. Mounting a floppy is a simple matter of inserting it into the slot of a disk drive. Just like hard disks, the information is stored in sectored tracks, which can be randomly accessed. The small circular hole above the central one marks the beginning of the tracks and acts as a reference point for reading and recording information. The long oval slot below the central hole enables the read-write head to come very close to the disk rotating rapidly beneath it. Although they are more expensive than cassette systems, disk drives form an important part of many microcomputer installations because they do not suffer from many of the limitations imposed by cassettes. They can hold far more information, and this can be transferred to the main memory much more quickly. Disks also tend to be more reliable and easier to transfer from one system to another. Compared to hard disks, of course, floppies are small and slow, although they are much cheaper and easier to transport. Of the range of computer media available, we have studied just three in this presentation: tape, disk, and drum. With their different characteristic features, one of them can usually be chosen to suit any particular application. What happens when extra storage capacity is needed in a system? One solution to this problem is to increase the number of devices, such as disk drives, which are already being used. Another approach is to try to eliminate the delays occurring when new tapes and disks are mounted. For example, in an airline reservation system, where there is a demand for virtually immediate access to a large volume of information, mass storage devices may be used. These allow the computer to take over the role of the human operator by being in direct control of the storage unit selection. The rapidly developing techniques of microelectronics offer another approach to the problem of information storage. Semiconductor devices are extremely small and fast, and as prices fall, they will be able to offer a realistic alternative to the conventional magnetic media, tape, disk, and drum.